Welcome to Conceptual Physics at Delaware Tech, Chapter 5, Newton's Third Law of Motion. So in this unit, we're going to cover forces and interactions. We'll talk about Newton's third law. This is the law of action and reaction. We'll talk about vectors and the third law. We've already talked a little bit about vectors. We'll kind of do some reviewing and how it relates to the third law. And then we'll do a quick summary of all three of Newton's laws of motion. So forces and interactions. An interaction is basically a force. It's a pushing or pulling between one thing and another. And in every force, every action will require a pair of forces acting between two objects. So anytime there's an interaction between two objects, your hand on a wall or your feet on the ground as you're walking, it's always a pair of interactions. The interaction of your hand pushing the wall, but the wall is also pushing you back. And this is referred to as a force pair, sometimes a co-pair, but I'll try to call them force pairs. So every force comes as part of a pair of forces. And these constitute a single interaction. So whenever one object, like a hammer, exerts a force on a second object, like a peg or a nail, whatever you're hammering, the second object will exert an equal and opposite force on the first. Now, this may seem counterintuitive. It doesn't seem like everyday thinking about a hammer hitting a peg. One thinks, oh, the hammer is doing the striking, it's doing the forcing onto the peg. But the fact is, anytime there's an interaction between any two objects, between a person and the ground, between an animal and a tree, any two things, a planet and another planet, the one force from one object onto the other will always be exactly the same magnitude as the force from the second object onto the first, just in opposite directions. So in this case, the hammer is putting a force on the peg, but the peg is putting an equal and opposite force on the hammer anytime there's an interaction. So, quiz question. A soccer player kicks a ball with 1,500 newtons of force. The ball exerts a reaction force against the player's foot of somewhat less than 1,500 newtons, 1,500 newtons, somewhat more than 1,500 newtons, none of the above. Well, I hope from what I just told you, you would know that anytime an interaction happens, there's an equal and opposite reaction force by the other object onto the first object. So the answer is 1,500 newtons. Newton's law tells us one object exerts a force on the second exerts the exact same magnitude force on the first. So the foot exerts a force on the ball, but the ball is also exerting a force on the foot. When you kick a ball, the ball feels that force, but you feel the ball hitting your foot as well. And it's the same amount of force. Now, this is a very, very important point, this third line in the explanation. It's important to note that the two equal and opposite forces are directed towards different objects. Why am I telling you this? Because this is a point I didn't quite get when I first learned this topic, and it really struck me as, how can anything move if they're always equal and opposite forces every time a force happens? Well, the way things move is you only look at the forces on that object. And when you have force pairs, one thing is A is acting on B, and B is acting on A. But if you're looking at A, you only care about the force B is putting on A. You don't worry about the other force. That is what directs the motion of A. It's whatever's forced onto A, that's what directs the motion of A. Whatever's forced on B directs the motion on B. So they direct motion on different objects, but they come in pairs. So action and reaction forces. Summary. One of these two forces is typically called the action force. The other one's called the reaction force. Now, don't get hung up about these words because they have nothing to do with cause and effect. We just looked at a foot kicking a ball. Normally, our notion would be to say, oh, it's the foot hitting the ball, that's the action, and the ball hitting back, that's the reaction. And that is what happens. But in physics, it doesn't really matter. The two are contacting one another. They're both exerting the exact same force on the other object. So either one can be called the action or reaction in this case. They're called force pairs, as I mentioned before, sometimes co-pairs. You can't have one force without its force pair. You can't have one force without the other. They're always in pairs. Sometimes I'll show you a diagram and I won't show you the other pair because it just complicates the diagram, and we're only interested in forces on one object, not the forces that one object puts on other things. So, but you always have to keep in mind every single force everywhere in the universe comes in pairs. So the pairs are found at every interface between two interacting objects or surfaces. A hand hitting a wall, a ball hitting a baseball bat, an atom hitting another atom. All of these things are interactions that involve force pairs. Whatever's hitting the other, they're both putting the same amount of force on the other, but it's just in opposite directions. They're equal strength, equal magnitude. So again, always remember they're on different objects. And I'll keep hammering this in because it's such an important point to understand why there's any motion if you always have these pairs. So Newton said to every action, there's always an opposed equal reaction. The more common way people think about this is for every action, there's an equal and opposite reaction. Just remember that it's A acting on B is the same force as B acting on A, just in opposite directions. So another example, you're driving in a car. The reason why the car, the most proximate reason why the car is moving, in other words, we're not talking about the engine turning the wheels, etc., but ultimately the wheels turn, the wheels push against the road. The tires are pushing against the road, and the road exerts a friction on the tires. If the road had no friction and the tires had no friction, there wouldn't be any way for the car to move forward. So the tire is pushing backwards against the road as it's turning, and the road is pushing forward with its friction on the car, and that's what drives the car forward ultimately. So, simple rule to identify action and reaction. First, identify the interaction. One thing is acting on another. Doesn't matter which one you say is interacting on the other, both are putting force on the opposite one. So one action could be object A exerts a force on B, and reaction could be object B exerts a force on A. It's always the same objects. You never involve a third object to determine what the action-reaction pair is. Another example, you have a rocket. It's shooting out gas from its fuel, and it's shooting it out the back of the rocket, and that's propelling the rocket forward. So the action is that the rocket exerts a force on the gas. It's pushing the gas out of the rocket. Well, at the same time, the gas is pushing the rocket forward. And that is ultimately how a rocket moves. And one of the ways we know this is that the gas from the propellant is pushing the rocket and not the air around it. A lot of people sometimes think, oh, rockets work because they're pushing air out the back, they're pushing gas out the back, and that's pushing the atmospheric gas back, and that's what's driving it forward. But the fact is, rockets work perfectly well in the vacuum of space, in deep space. They don't need any other matter. It's just that mass being shot out the back of the rocket because the rocket is pushing the mass out from that chemical reaction in the rocket or whatever's happening with the propellant. It's pushing it out, and in turn, the gas is pushing the rocket forward. And that's what drives the motion of these rockets. So, question. When you step off a curb, the earth pulls you downward. That's gravitational pull. The reaction to this force is A, a slight air resistance, B, non-existent in this case, C, you pulling the earth upward, D, none of the above. Well, remember, here we're talking about an action force of the earth pulling on you. Well, it turns out you're pulling on the earth with exactly the same force. That's what Newton's third law tells us. If one object's exerting a force on the second's exerting an equal and opposite force on you. If you weigh 500 newtons, in other words, the force of the earth pulling you down towards the center of the earth, your weight is 500 newtons, you are also exerting an exactly identical sized force, just in the opposite direction, pulling on the earth with 500 newtons. So the two forces are exactly equal. Now, just to remind you, all matter, including you, have gravity, okay? All matter has gravity. You don't notice it because the gravity is dependent on the masses of both objects. So in the case of the gravitational force between you and the Earth, it's dependent not only on the Earth's mass, but also you. But the fact is you're so small compared to the Earth, it's not as important in the calculation, but it still is in the calculation. They're actually multiplied by one another, so I guess they really are more important. I shouldn't have said that. As well as the distance between the two of you. Now, you might say the distance between you and the Earth is nothing. You're standing on the Earth. It's always between two objects, between the center point of the two objects. So when you're doing calculations later, when we do more advanced calculations of gravity, it's between you, and you can say the center of you is the center of your body, and the center of the Earth. So you're never at the center of the Earth, obviously, unless somehow we bored right through the Earth. And we'll talk about that theoretically. But the distance when you do these calculations is always between the center of any object. So if we're looking at the gravity between the Earth and the Moon, it's the distance between the center of the Moon and the center of the Earth. When you step off a curb, the Earth pulls you downward and you pull the Earth upward. We just established that. Why don't you sense the Earth moving upward towards you? A, Earth is fixed, so it cannot move. B, Earth can move, but other objects on it prevent it from moving. C, it moves, but by a very small amount that you cannot see. D, none of the above. Well, it does move, but it's an insanely tiny amount. The force that the Earth exerts on you is exactly equal to the force you exert on the Earth. That's Newton's third law. But the fact is you will move much more than the Earth does. Why? Because you have much less mass than the Earth does. Remember, force equals mass times acceleration. That's Newton's second law. Well, if we have the same forces on the Earth by you and on the you by the Earth, and they're both equal to m times a, well, the Earth's m, the Earth's mass, is 23 orders of magnitude bigger than your mass. In other words, take whatever your mass is and add 23 zeros to it. That's the mass of the Earth. And as a result, your acceleration, that 10 meters per second squared that you feel when you fall with gravity, that is 10 to the 23 times bigger than what the Earth feels. So the Earth, if you actually do the calculations, and I wouldn't worry too much about the calculations, just understand the concept here. Your movement is 10 meters per second squared. That's your acceleration due to gravity. The Earth's acceleration due to gravity is 1 times 10 to the minus 22 meters per second. That works out to, if you wait for the time of the acceleration to go on, it's still less than the width of a proton. So you don't notice it because it's impossible to notice. So action and reaction on different masses. This is what we were just talking about with you and the Earth. You can also talk about it with a cannonball being shot out of a cannon. The cannonball weighs maybe a few kilograms. The cannon weighs hundreds of kilograms. So they experience exactly the same force. The force of the cannonball being shot by the cannon and the force of the cannon recoiling because of the cannonball. So the same force, remember, force divided by mass equals acceleration. I just said force equals F equals ma. Well, A equals F divided by m. So acceleration is force over mass. If it's the same force and you have a small mass, you're going to get a large acceleration. With the cannon, it's the same force with a large mass and you'll get a small acceleration. I hope I said that right. So the same force on a small mass will produce a large acceleration. The same force on a large mass will produce a small acceleration, as long as these are force pairs that are exactly equal in size of force, but in opposite direction. When a cannon is fired, the accelerations of the cannon and the cannonball are different. The accelerations are different because A, forces don't occur at the same time. B, forces, although theoretically the same, in practice are not the same. C, masses are different. D, ratios of force to mass are the same. Well, I think we already said it's the masses. The cannon weighs much more than the cannonball. It has much more mass than the cannonball, and therefore it is more sluggish. It has more inertia. It is more sluggish to the same amount of force, and therefore will accelerate less. And in fact, when you make cannons, you make them purposely really big and heavy so they don't recoil that much. They will recoil. You never want to stand behind a cannon when it's being shot off. It'll spring back. But the cannonball gets much more acceleration forward as it's being shot out. And that's Newton's third law combined with Newton's second law. The acceleration of the same force is because of Newton's third law. The acceleration is the force divided by mass. That's Newton's second law. So they really work together hand in hand here. And you end up with different accelerations when you have different masses. Consider a high-speed bus colliding head-on with an innocent bug. Okay, everybody's driven in a car and seen a bug splash against their windshield. The force of impact splatters the unfortunate bug all over the windshield. Which is greater, the force on the bug or the force on the bus? The force on the bug, the force on the bus, both are the same, cannot say. Well, I think by now you know that even though it seems a little weird, they're exactly the same force. Newton's third law tells us the bug is exerting exactly the same force on the bus as the bus is on the bug. Why doesn't the bus get as damaged as the bug does? Because the bug will experience a much greater acceleration, crushing its body, whereas that change in acceleration in the bus is pretty much imperceptible to any driver. It's just a tiny, tiny change because the mass of the bus is so much greater than the mass of the bug. If the bus is 1,000,000 times more massive than the bug will experience 1,000,000 times greater acceleration than the bus will. They're inversely proportional. Two people of equal mass on a slippery ice, so no friction here, push off from each other. Will both move at the same speed in opposite directions? A, yes. B, yes, but only if pushed equally. C, no. D, no unless acceleration occurs. Well, the answer, I hope you got it by now, is yes. It doesn't matter who pushed who. The exact same force will be exerted on both people. Bob could push Kathy, or Kathy could have pushed Bob. They will both feel exactly the same action and reaction forces, and therefore will be accelerated due to those forces. Since they have equal masses, they will get equal acceleration in the opposite direction. Next time you're on the ice, you can test this out for yourself. So no matter how they push, it's still going to be the same thing as long as they have equal masses and as long as you're pushing head on, you're not glancing somebody. So this produces equal accelerations because they have equal mass. If they didn't have equal mass, this wouldn't be the case. They'd have different accelerations. So Newton's third law, we're going to continue, but we're going to use a concept called free body diagrams. These are basically diagrams where you're looking at all the objects interacting, and you essentially put a little box or a circle around just the thing you're interested in the movement of. So I've got an orange in a cart. It's a living orange. And this cart is being pulled by some external force. So which objects are in the system, which objects are outside of the system. In this case, the orange in the cart is the system. So they act as one unit. And we are interested in all the forces that act on that orange in cart. We don't care about the forces the orange in cart acts on other things. We just care about what forces are acting on this system of the orange in the cart. And that will determine the movement of that system, that object. So we look for the external forces on the system. There might be internal forces. There definitely are internal forces. Every time you have any molecules, the molecules inside the orange are bouncing around, but they are hitting each other, and internal forces do cancel each other out, but external forces do not. Because internal forces, remember, it's one part of object A is acting on a different part of object A, and then that different part of object A is acting on the first part of object A. So since they're both internal to whatever system we defined, they cancel each other out. And this is an important distinction to make here. So we're going to consider this enclosed orange in the cart. We're applying an external force, and we will only see the action force here. We're not looking at the reaction force of whatever's pulling the orange cart, okay? So now we'll look at what is pulling it. Okay, so we've got this anthropomorphic apple, an apple that's like a person here with legs. And the action and reaction forces don't cancel. Why? Because they are external to the system we're interested in studying right this minute. We put a box around the orange cart. Okay, so we're only interested in the forces on the orange cart, and that's the arrow pointing away from the orange cart. You'll see there's also an arrow pointing away from the apple. That is the force that the orange cart is exerting on the apple, but that doesn't affect the orange cart. It's what the orange cart did, but it's not what's being done to the orange cart. And that's what we're concerned about when we're looking at the motion of a system. So the external force is the one pulling on the orange cart. Could be pushing, but it's acting on it. So now let's look at a different version of the system. Now we've got an orange cart being pulled by the apple, but we're going to say the whole thing is our system of interest. You might go, okay, well, wait a minute. How does anything move? Because you just said that the internal forces, which these two are now, cancel. Well, they do cancel, but that's not what drives the movement of the whole system. So they're no longer external, they're internal. They internal force pairs because they're both acting on different parts of the same quote-unquote object, what we call system, and therefore they do cancel out. So a stationary tire that's full of moving gas is another example of a lot of internal forces canceling. If you fill a tire or a balloon with gas molecules are moving all over the place. But ultimately, if you add up all the forces inside there, they cancel each other out. We know that because there's no movement of the tire unless it's acted on by an external force. So the various forces within a system will always cancel. You don't generally have to worry about them. Without external forces, there is no acceleration of the system. In this case, the system is the whole thing, the orange cart connected to the apple. So how does it move? We know it does accelerate. Those cancel, the internals cancel, so it's not that. But there's also an external pair of forces, one that's acting on the whole system and one that's the system is acting on, which we don't care about. Well, that force pair is, look at the apple's feet. They're pushing outside of the system. The feet are pushing on the ground, on the floor. So as the feet are pushing on the floor backwards, remember when you walk, you're pushing your feet backwards so that you drive your body forward. When tires turn, they're turning in such a way that the surface of the tire is hitting the ground going backwards to drive the body of the car forward. So in this case, the apple is walking, pushing on the floor. Well, that doesn't change the movement of the system because that's not acting on the apple-orange system. It's the floor acting on the apple, which is part of the apple-orange system. It's the floor's friction acting on the apple. Now, that's what's driving the motion forward. Now, you might say, well, wait a minute. In the past unit, you said friction is always in the opposite direction of motion. Well, it actually still is opposite direction of motion, because what is actually moving here? The feet are moving against the floor backwards, so the floor is pushing the feet forwards. And the feet are connected to the apple's connected to the orange cart, so they all go forward. But it's because of the movement of the feet going backwards, friction drives them forward. And anytime you walk, that's what's actually happening. And that is the reason why you can't walk on a super slippery floor. There's no friction to push you forward when you're pushing back. So one of these external forces is an act by the system, which we don't care about usually. That's acting on the floor. We don't care what happens to the floor generally. The other is the external force acting on the system. That's the floor pushing back on the apple-orange cart system. And that's what drives the apple-orange cart system forward. The friction of the feet against the floor. So external forces push the system forward and will accelerate the system. When I say accelerate, I mean you start from nothing and you go up to a faster speed, and you could slow down and stop at that point, but to get started you have to accelerate initially. So this is the second force pair, the one of the two external forces of the force pair is what drives the whole system. It's always external forces that drive the system. Internal forces are canceled. So the apple-orange system will move at a constant speed. Okay, lights should be going off for you when you hear constant speed. If A, the orange loses mass, B, the apple loses mass, C, there's also a force equal and opposite to the friction force, D, none of the above. So when will it move at constant speed? Well, the second you see constant speed, you should think, oh, net force is zero because net acceleration is zero. Constant speed means zero acceleration. Zero acceleration means zero net force. So as soon as you hear no net force, that means whatever force you do know about must be counteracted by an equal and opposite force. We are not talking about the reaction pair here. We're talking about some other force that happens to be equal to the force of the floor pushing the apple-orange system forward. This is not the Newton's third law pair. This is just some other system. Otherwise, you wouldn't be able to get this apple-orange cart moving at a constant speed. Remember, constant speed means the forces on the apple-orange are counteracted by other forces on the apple-orange. We don't care what the apple-orange does to other things. That's a force pair. We're not talking about a force pair. So there must be some other force we haven't talked about yet to equalize the two forces so that the net force is zero, so that the net acceleration is zero, so that the speed becomes constant. Constant could be zero, or constant could be positive, or constant could be negative. As long as it's constant, it's not changing. No acceleration. So this force could be something like other friction forces on the system, like the wheels of the cart are scraping against the ground and slowing it down so that it's not accelerating anymore. It's just going at a constant speed. Even if you're putting a constant force between the apple's feet and the ground, there's also this constant force backwards of the friction between the wheels and the floor. That could be one possible explanation. You could also have a headwind blowing into the apple, and it's producing a air resistance force that we talked about when you're falling, but it could be in the direction facing them, a headwind, and that force could be preventing any acceleration. It would be an equal and opposite force. It doesn't necessarily stop motion, it just stops acceleration of motion. All right, so when lift is the technical term for an upward force that a plane or a helicopter or a bird might use to push air in order to rise up in the air. If the lift force equals the weight of the helicopter, remember the weight of the helicopter is the downward force. The helicopter A climbs down, climbs up, C hovers in midair, none of the above. Well, you might think, oh, it's equal, it can just rise up. Well, remember, it's equal. So equal means the forces are even, and therefore there's nothing accelerating it up, there's nothing accelerating it down. When you say climbs down and climbs up, this question probably should be worded better. These are the questions from the author. I think they really mean accelerates up and accelerates down. And in fact, what they do instead is it hovers. And in fact, that's how a helicopter will hover. It produces a lift force that pushes it up with exactly the same force as the gravity, the force of gravity pulling it down is. In other words, force of gravity in this case is the weight of the helicopter. So the upward force, that's the force from the helicopter rotor blades spinning and pushing air downward, is equal to the downward force, the weight of the helicopter. And therefore, if the force is canceled, the net force is zero, so there's no upward or downward acceleration. And if it's already in the air when this happens, it's called hovering. If it moved at a constant speed, up or down, that would still be not an acceleration situation, okay? So that could have happened as well. That could have been another correct possible answer. It could have been that it was just moving up in a constant speed or down in a constant speed. And I know that's misleading in this question. Probably should be worded better, and I'll change that. When the lift is greater than the weight of the helicopter, okay, now this is a more definite situation. The helicopter A climbs down, climbs up, hovers in midair, or none of the above. Well, I think by now you know that if the force up is greater than the force down, the net force will be up, and the helicopter will climb up because a net force is up. That means the net acceleration will be up, and the helicopter will rise at a faster and faster rate. A bird flies by A, flapping its wings, pushing air down so that the air pushes it upward. C, hovering in midair. D, inhaling and exhaling air. Well, hopefully by now you realize from the example of the helicopter that it's doing similar things. In fact, helicopters were designed in part due to studying the motion of birds and some insects as well. In fact, this went back to the time of Galileo. Da Vinci. Da Vinci used to study the motion of birds in order to design. He actually designed helicopters. He never built them and made them work, but he actually has drawings of helicopters or helicopter-like planes from hundreds of years ago, long before the invention of a working plane. So I think you know it's pushing air down so that the air pushes it up. This is Newton's third law. If you push air down, the air will push you up. And this happens with birds, it happens with planes, it happens with helicopters. So the lift is achieved by the bird pushing enough air down. That's the reaction force is the air pushing the bird back up. The more air it pushes down, the more upward lift it generates, and the more it accelerates up. By varying how much air the wings push down, and that birds do that by both flapping and twisting their wings in certain orientations, they can control whether it climbs in the sky, stays level, hovers, dives down, which would be accelerating downward, or just gradually going up. So it's constant acceleration, zero acceleration, constant velocity up or down. That would be if it equalized the two forces. The slightly tilted wings of airplanes deflect A, oncoming air downward to produce lift, B, oncoming air upward to produce lift, C, both A and B, D, neither A and B. Well, I think we've been talking about this. They are pushing air downward so that the plane goes up, moves upward. So the wings are actually shaped in such a way to divert air downward, and they're built into the plane at certain angles, and they're shaped a certain way to push the air downward. And this will drive the air down, and the air will drive the plane up. That is Newton's third law. It's not the only explanation for a plane flying. There are actually multiple things, but this is one of the big important explanations of why planes even work. So how do you swim upward when you're in the bottom of the pool? It's the same thing. You're pushing water down with your hands. You're pushing water down, and your body will start popping up to the top. Of course, You also have buoyant forces that are pulling you up, and we'll talk about those in another unit, unit 12, I believe. No, unit 13. But this is just another example. You floating and hovering around in water by pushing different amounts of water down, different forces pushing down that in turn create forces pushing you up. The vertical component of an upward force with both, usually with gases like the air, is called lift. The horizontal component, which is the plane going into the air and feeling the force against it, usually pushing backwards, that's called drag or air resistance. So it's similar to the resistance of when a skydiver is falling through the air. There's air resistance pushing up on them. When a plane is flying through the air, there's air resistance, drag pushing back on them as they're flying. Compared with a light wing glider, a heavier glider would have to push air. So we're looking at the heavier glider. The heavier glider will have to push air downward with a greater force, downward with the same force, downward with less force, none of the above. Well, remember, this is a heavier glider. It weighs more, it has more downward force, and therefore to fly in the air, to hover in the air, it must have a greater downward force that's pushing the air down, so it has a greater lift pushing this heavier glider up. So the force of the air deflected downward has to equal the weight of the glider. The heavier glider must deflect air downward with a greater force than the lighter glider does, so that they both end up either moving up, accelerating up, or even hovering. It's just a greater threshold they have to reach. Now, we talked about this many times before, so I'm going to go through this pretty quickly. Vectors, we know, are quantities that have both magnitude and direction. We usually represent them with an arrow if we're drawing them. And we've already done examples: velocity, force, acceleration, and later we'll talk about momentum as well. These are all vectors because they have a direction. They point in a certain direction. Scalar quantities, these are the ones without direction. They still have size, magnitude. Speed, mass, volume, energy, these are scalar quantities. We've talked about this before, how to add up vectors. If they're in the same direction, add them arithmetically, so you just add them together and it's pointing in the same direction. If they're in opposite directions, subtract them, and whichever one is bigger of these arrows, that's the direction of the net force. If they're not in line with each other, they make an angle between each other, use the parallelogram rule. We've talked about this before. You'll use the diagonal, will give you the resultant, and you can do this by just drawing quick and dirty to figure out where the resultant force is. If you have the resultant, you can come up with the parallelogram if you know the direction of the other two forces. You could just make a parallelogram that will match your diagonal's direction and magnitude. If they're right angles, this is an even easier situation. Your parallelogram is now a rectangle, and in the rectangle case, you can just look at half of the rectangle as a right triangle and use Pythagorean theorem to calculate your diagonal, your resultant vector. We've seen this kind of diagram before. We're going to talk about slightly different questions here. So referring to the figure below, we've got a 30 Newton force pointing up, we've got a 40 Newton force pointing to the right, and we've got a 50 Newton force pointing at a diagonal upward right. So it says which one of the following is correct. 50 Newton is the resultant of the 30 and 40 Newton vectors. The 30 Newton vector can be considered a component of the 50 Newton vector. The 40 Newton vector can be considered a component of the 50 Newton vector. All of the above. Well, I think we already know they're all of the above. The 30 and the 40 are components of the 50. They vectorially add up to become the 50 using Pythagorean theorem. You create the right triangle, and you can do the calculation and get 50. 30 squared plus 40 squared equals 50 squared. You've seen this one before too, but we're going to ask a different question on this one. So given the figure below, which of the following is true? Now look at the figure first. We've got a plane, we'll say the upward direction is north. So you got a plane in its original heading going 80 kilometers per hour due north. But there's a crosswind shown at the bottom pointing east. So it's perpendicular to it at 60 kilometers per hour. And the resultant vector, if you use Pythagorean theorem, is 100 kilometers per hour. Okay, so the question is, which of the following is true? 100 kilometers per hour is the resultant of the 80 and 60 kilometer per hour vectors. The 80 kilometer vector is a component of the 100. The 60 component vector is a component of the 100. Or all are true. Well, I think from the last example, you already know the answer that all are true. If we create our rectangle, we create our diagonal to make a right triangle, we can quickly use Pythagorean theorem. The square root of the sum of the two side square roots is the amount of the diagonal, the hypotenuse. So the square root of the sum of the squares of the legs of the right triangle, what we call the legs of the right triangle. The legs would be the 80 kilometer per hour vector and the 60 kilometer per hour vector, and we get 100 kilometer. And use your calculator to prove to yourself that this is true. Since the sum of the heading vector and the crosswind vector equal the resultant, the first two vectors are called components. And components could be perpendicular to each other. They don't necessarily have to be. Frequently, they'll be designed to be perpendicular. So say somebody gives you a diagonal vector and they say, what are the components? And you want the y component and the x component that add up to the vector. But sometimes they may want different vectors to add up to the one you're interested in. They might be an x and a y, but the x and y might both be tilted. And that might be useful when you're looking at inclined planes or slopes. Here's another example you saw before without the diagram. So maybe the diagram will help you a little bit. You run horizontally 4 meters per second into a vertically falling rain that's also falling at 4 meters per second. Of course, that's perpendicular. Relative to you, in other words, you don't see yourself running. You just see the drops coming at you. The raindrops are falling at an angle of 0, 45, 53, or 90 degrees. Well, if you saw the last video, you already know the answer is 45 degrees. And the reason for that, a little trouble here. The reason for that is that relative to you, the rain is not only moving downward, but it's also moving toward you. Make believe you're not moving, the rain looks like it's moving at you. So you have two vectors the rain appears to be doing from your point of view. And when you add those two vectors together, you get a resultant that's pointing downwards towards you at a 45-degree angle. If you use Pythagorean theorem, you'll find that 4 squared plus 4 squared equals about 5.6 meters per second, that quantity squared. So use Pythagorean theorem to prove it to yourself. So since they're perpendicular, you can use the Pythagorean theorem. But the fact is, you see it's 4 down and 4 across. You know it's a square, so you know the angle is 45 degrees. We've seen this one before too. Nellie Newton's hanging from a rope. It's actually from 2 ropes here. Which side is greater? She's got the force down due to her weight. She's got a tension on the left cable, a tension on the right cable, which are not drawn to scale. We talked about this last time, how to figure this out. I'm just reminding you. You create a parallelogram that matches the opposite force that must be holding her in place. So if her weight is down, there must be an opposite force up. And the only sources of that opposite force are the 2 cables pulling up. So they must have forces on them that will add up to vertical. And the way to do that is use the parallelogram rule shown in the green here. And you can just, once you know the sizes of those, you can just move them so that they line up with the cables themselves. And you can see the size of the 2 vector forces, the 2 tensions in the 2 cables that are counteracting. And if you were to mathematically add up the 3 different forces, T sub L, T sub R, and the weight force, mathematically, they all will cancel. They'll cancel in the vertical direction, they'll cancel in the horizontal direction as well. That's because the 2 cables their horizontal components are exactly opposite each other. The weight has no horizontal components, straight down. But all the forces will cancel, and as a result, Nellie stays still. She's not accelerating up or down or to the left or to the right. She's in place. So now here's one you haven't seen before. So we're looking at vector components of, say, throwing a ball in the air. The vertical and horizontal components of the resultant vector are perpendicular to each other. So if we're interested in an object moving through the air and it's curving, whatever, at any one time we want to know, to keep it simple, we'll only look at the vertical forces each time. And then we'll only look at the horizontal forces. In this case, we're looking at velocity. So we're only looking at the vertical component of the velocity each time, which you'll notice the vertical component, as it's reaching the top, is getting smaller and smaller. That is because it's slowing down in the vertical direction. If she had thrown the ball straight up, it would just go up and slow down, come to a dead stop at the top, and then start accelerating back down. So it would be going as fast before it hit as when she threw the ball originally. So you have the vertical component, just focus on the vertical first, and then once you figure out how long it takes to do the vertical and what happens there, then you look at the horizontal. Well, there's no force stopping her horizontal. We're going to ignore air resistance here. The horizontal velocity that she imparted on the ball, you'll notice the size of the blue line that's horizontal, that's the flat one. It's exactly the same size in every position of this arc that the ball is traveling over. It never changes. But the vertical one starts off big, gets smaller and smaller. At the top, it's nothing, and then it gets bigger and bigger because it's getting faster and faster, but in the downward direction. And that is because of the acceleration due to gravity. She gives it an initial velocity up. Why is the velocity changing? Because there's a force acting on it. The only force acting on it is the force of gravity, which makes it slow down, slow down, slow down, slow down, come to a dead stop, speed up in the opposite direction. So it's always been slowing down by the same amount. It's losing the same speed. It's losing 10 meters per second every second. Eventually it'll get to zero, and then it'll be negative 10 meters per second, negative 20 meters per second, negative 30 meters per second, as it's coming down for every second of the movement. If you wanted to do this in a more mathematical way, you would have to use trigonometry. Again, we don't do that in this class, but you should be aware of what's actually happening in a physical sense. So here's another vector situation. You've got Nellie pulling her sled, and you'll notice she's pulling her sled at an angle, okay? That force that she's pulling is noted F. That's the solid red line, the solid red arrow. That's the force she's pulling on the sled. And that force is at an angle, so there's a vertical component to where she's pulling and a horizontal component. And so while she's pulling at an angle, it's really as if there were two pulls, one pulling straight up and one pulling directly to the right. But when you add those two together, you get the force along the rope that she's holding to pull with that tension along that rope that's labeled F. So at the angle she's using, it's shallow enough that the two forces, the vertical force and the horizontal force, are different sizes, different magnitudes. And by looking at the picture with the angle shown, which component of her force is greater? Well, I think you can see that it's the horizontal component, what we call the force in the X direction. So why is this angle good for her pull? Well, think about it. If she pulled higher, much of her effort would be lifting the sled up and not actually dragging it forward. You have to lift it a little bit because of the friction of the ground. That's absolutely necessary. You have to get it off of the ground so there's less contact and less friction force on there. But you also have to pull it forward because the friction is actually in that direction of movement. So there has to be some angle there. Can't be completely flat. It can be, but it's much harder to pull. It can't be completely straight up or she won't pull the cart anywhere. She'll just be lifting it off the ground. So having it mostly in the direction she wants with a little bit in upward direction helps her pull forward, as well as helps minimize the amount of friction that will be actually there. So what other forces not shown act on the sled? Well, we've been talking about the friction between the sled and the ground, but there are also forces between There's also the weight of the dog on the sled. There's the normal force of the ground holding the dog and sled up. Otherwise, the dog and sled would accelerate right into the earth. We also have the friction that we've been talking about. What force allows Nellie to move? We haven't talked about that one. Remember the apple walking on the ground? Look at her foot. Her foot is, her left foot, the one in the back, is pushing against the snow, pushing against the ground. So as she's pushing against the ground, the snow is, the friction of that surface is pushing against her and driving her with the cart forward. So that pink arrow there, the force of the snow's friction on Ellie, is what is it's the external force on the system that's actually driving all of them forward. So normal forces, weight versus normal force. Normal force we abbreviate as N frequently. Sometimes it'll be F sub N, but N is the more common one in this course. N is always perpendicular to the surface, to the ground. Now, you might think, okay, that means pointing straight up, but on a slope, it's still perpendicular. So if you look at the pictures on the bottom here, you have a block of ice sitting on the ground. In the first picture, the block of ice is sitting on flat ground, so the normal force is exactly pointing up, and it is identical to the force of gravity pointing down. But as you have ground that's tilted more and more, the normal force is still perpendicular to the surface, but it's not in the same orientation as the weight. You'll notice the weight is always pointing down towards the center of the earth. But the normal force depends on the surface that the object is sitting on. And so look at the first question here. As the ramp angle is changed, which force remains constant? If you look at the sizes of the arrows, you can see the weight force, that's not working, whoops. The weight force, W equals mg, mass times gravity, is the same every time. Why? Because it's not changing its weight. Whatever orientation it's in, the block has the same mass, there's the same gravity, so it has the same weight. Question 2, as the ramp angle is raised, how does the magnitude of N change? How does the magnitude of the normal force change? Well, if you look at the pictures, you can see that as you tilt it more and more, the normal force is smaller and smaller. And that is because there's less force of that object pushing against the wall. As you tilt the wall, or tilt the floor in this case, there's less of the normal force that's being of the block of the ground pushing against the block. That's what it is. It's the ground pushing against the block. There's less and less as you tilt it more and more, and eventually it becomes nothing. And that's why things just fall when they're either just sitting up against a wall or sitting all by themselves in space. In the air, they'll just drop. So the normal force is 0 in that case. So when the ramp is raised all the way to 90 degrees, I just said this, the net force is just the weight force, mg. The normal force is nothing by that time. You've tilted it so much that the ground is not able to put any force on the block, because that's what the normal force is. It's the force of the block, it's the force of the ground, no matter what its angle is, against whatever's sitting on the block. Well, if it's barely sitting on the block, there's barely any force against it, and that's why the normal force gets smaller and smaller. All right, 2 forces act on Nellie on a slope. The weight, which is W equals mg, and the normal force, N. Can you see that N and mg are equal and opposite in figure A? So in figure A, the arrows are supposed to be pointing from the center of her body. So you can see if you start from the center of her body, the arrow down, the weight is exactly equal to the arrow up, the force of the ground against her body pointing up. Yes, the arrow should start from the ground, but it's a force on her body, so we start it from the body. And that might be a little confusing to you as well. As you tilt the ground in figure B, it says, can you see that N is less on the incline with figure B? Well, now the ground is not able to put as much force against her because the ground is tilted. And therefore, the N is going to be less. The normal force is going to be less. the weight doesn't change. She still weighs the same amount pulling her down. But if you look at it, you can see the weight, it's written straight down. But if you imagine a world where you're looking from the angle of the slope, so let's say you're standing on the slope, weight doesn't look like it's straight down. Weight looks like it's at an angle. And so if you decide what are the components of the weight, you can see the two black arrows that I've shown, two dotted black arrows in figure B. Those are the arrows that represent the components of the weight that we call the parallel and perpendicular components. So one of these arrows is perpendicular to the surface of the incline, and one of them is parallel surface of the incline. And a lot of times physicists that are interested in using trigonometry to solve these problems, you don't have to do this, they will break up the weight into two components, one that is directly perpendicular to the surface and one that is parallel with the surface. So the one perpendicular to the surface has to match in the opposite and equal and opposite direction to the normal force. And that's actually how you calculate the normal force. You look at the weight and say how much of that weight is perpendicular to the surface. That is what the normal force will be pointing in the opposite direction. And the other component that's parallel to it is the force driving the person or object or block down the slope. So that's why we break it up into those two components. And that's what's represented in both figure B and figure C. So in C it says, can you see that the resultant of N and G is the force propelling Nellie down the hill in figure C? Okay, so what does that mean? Well, if we've got the weight component broken into a component that's in the same direction as N, we could just add and subtract those. If it's perpendicular, that's what's left over. Because if you have a normal force pointing this way and a weight pointing down this way, the weight has a component that's also pointing in the same direction as the normal and completely perpendicular to the normal. Well, the one that's pointing exactly in the same direction, the what looks like the sort of downward arrow in B, is equal and opposite to N. Those cancel out. They become zero. So what's left over? It's the other component of the weight force, the one that is pointing down the slope. So in B, the only remaining force is the one driving Nellie down the hill. So the resultant is what is not canceled out. That perpendicular component of the weight is canceled out. The horizontal component, the parallel component of the weight is not canceled out, and that is what drives her down the hill. So to review the three laws of motion, an object at rest remains at rest, and an object in motion tends to remain in motion at constant speed along a straight line path. This is Newton's first law of motion, also known as the law of inertia. In other words, an object has mass, it has inertia, it has a sluggishness towards being accelerated. It requires a certain amount of force to make it move faster, make it move slower, change its direction, and that requires force. And the bigger the mass, the more force it requires. The bigger the mass means the more inertia, the harder it is to move, the more force is required for the same acceleration. That's Newton's first law, and we represent that as saying if the net force is dead zero, we add up all the forces at zero, then the net acceleration on an object is also dead zero, and that means the object's either dead still or it's moving at a constant speed. It's moving at a constant speed. That constant speed could be zero. Zero is a constant velocity or a constant speed. Newton's second law of motion, also called the law of acceleration. When a net force acts on an object, the object will accelerate, and that acceleration is directly proportional to the net force. Why? Because A equals F divided by M. A is in the numerator on one side, F is on the numerator on the other. They're directly proportional. The mass is in the denominator of the other side, so acceleration and mass are inversely proportional. So in the case of acceleration and force, increase acceleration, you'll increase mass. Increase acceleration, you'll increase force. Decrease acceleration, you'll decrease force. Decrease force, you'll decrease acceleration. They work hand in hand. Change either one, they work in the same direction, up or down together. The acceleration and mass are inversely proportional. One's up, one's down. Double the acceleration, you will cut the mass in half. Increase the acceleration tenfold. You would decrease, to do that, you need to decrease the mass tenfold. Increase the mass tenfold, you will decrease the acceleration tenfold. It will become 10 times smaller. It's always times and multiplying and dividing when you do this. Don't ever add. Now, this equation is usually written as F equals ma. It's frequently better to think of it as A equals F over m. Understand that both can be important ways to think about it. I bring this up because Newton's third law, the law of action and reaction. Whenever an object exerts a force on a second object, the second object exerts an equal and opposite force on the first. And this is what we've been talking about. Force of A acting on B equals exactly B acting on A, except it's negative. It's in the opposite direction. And since both forces are identical, they're both equal to ma. This one's equal to its own ma pair, and this one's equal to its own ma pair. The m's may be different, so the a's will be different. If you have a high m, you have a low a. If you have a low m, you have a high a. And that's the combination of Newton's third law and Newton's second law. So all of these laws are really part of the same package of concepts. And I want you to think about this slide to get a real idea of how these all work together. And that's the end of the unit. Thank you very much.